Hello everyone, it is January 12th and it is a perfect time to do LeetCode problem 211, Design, Add, and Search Words Data Structure. Let's get into it. Design a data structure that supports adding new words and finding if a string matches any previously added string. Implement the word dictionary class. The word dictionary initializes the object. Void add word adds the word to the data structure. It can be added later. It can be matched later. Bool search returns true if there's any string in the data structure that matches word, or false otherwise. Word may contain dots, where dots can be matched with any letter. Example 1, we add these words, bad, dad, mad. We search for pad, which returns false. Search for bad, which returns true because it's already in the dictionary. .ad returns true because the dot can be replaced with either, or not replaced, but bad, dad, or mad fits the criteria because the dot can be replaced as a B, D, or an M. And then B dot dot returns true because this dot and this dot can be replaced with A and D. The word consists of lowercase letters, so we don't have to worry about finding a word like bad with a capital B and then comparing it with bad with a lowercase b. Okay, well, so we need a way to store these words so that in the future we could look up whether or not these words exist in that storage. And the first idea that I have is to use the try data structure, which stores a try data structure where we can store each letter in a word, and then if the letter is seen again, let me draw it out first. So we can store a B, an A, and a D, and the try data structure is essentially a tree where one node can have a specific letter, and also in the node can contain a next pointer which points to another node, and it can have many pointers. So B can point to A. B can also point to, let's say there's a U for some reason, or an I. And then we continually store a node and a character for each letter in the word. So if we have to add the word bad, we store B, and then we continue iterating through the word. We create another node where B points to A, and then continue iterating through the word, and A points to a node with the value D. And then if we were to have a word called bud, we would use the same node of B. We would search it in the tree, and then if U is not in a pointer for B, then we store it in B. Similarly, we do the same with I. Now, if there's a word like batch, for example, or I'll just say bat, B-A-T. B is in the tree, A is in the tree, T is not in the tree, so then we add it to T. But then say we will look for a word like badder. Well, no, say we look for the word bad in the future. B-A-D, and so that word is in the dictionary or is in the tree, and we're searching for it. So once we have found the complete word in search, then we can return true. And that can also stand true for if instead it wasn't bad, but say we previously stored the word batter. Then searching for the word bad would still remain to be true because we've reached the end of the word we're searching for, not necessarily the word we've added. So how does that work in the case of a period? So I'm thinking that if we have the word, I suppose for any letter that we've added, we could also replace that letter with a period. There will be at most 2 dots in a word. So if we were to add a B in batter, we could also add a period. And then once we add the A, we can add an A and everything in between. As long as they're only up to two dots. So we'll also add potentially dot D, or potentially dot A, I, D. So then if we search for bad, then we see that the tree contains the period, and we iterate downwards to A, and then downwards to D. And so then that fulfills the completion of the word we're searching for. So we could return true. So I guess the only thing that I am thinking of in terms of it could be a little complex is that when we're adding the word bad, we'll need to add the word letter by letter, but we'll also need to add the versions of bad that a period replaces the B and the A and the D. The word length is going to be up to 25. So if we were to have a word of length 25 and then we would have to replace each letter with a period at least once or potentially twice for each individual letter in the word, potentially. So that could be a little bit of an issue. We don't necessarily need to replace uh, each individual character with a period for each word, because since words like bad, dad, mad, pad, since they're only missing since the difference between them is only the first letter, we only really need to do a period one time for the first letter and then a d, or a period, and a d, or a period, an a, and then a period. So that helps a little with that, though I'm still not sure if it is the right solution. Nonetheless, I think using a try data structure is appropriate for this problem. Yeah, that's what I'm going to go with. So I need to implement a try data structure, and then I need to somehow recursively go through each index in the word bad, mad, or pad, and then replace up to 2 letters with a period, potentially just a 1. Okay. So now I have to implement a tree or a try. So I'll say, what do we need? We need a node first, class node, which will contain a value. Self.value equals to a letter. I'll say letter. And then self.children, which will be a dictionary containing nodes to the next letter or the next node. The dictionary containing nodes that correspond to the next letter in the word. So node B would be the initial node, and then we would store a node A in self.children, and a node containing U, and a node containing I. And then as we're traversing through the word we're searching for, we search if one of these letters is in a node in the children. And if it is, then we traverse through that node's children, and we continually do that. So we have a class node, and I can be more specific by saying try node. And then we'll have a class called try, which will contain a root. I'm just going to say initially it's none. And we need to do two things with it. We need to insert the word. I mean, this is technically already doing that. So I don't necessarily need to do, I don't need to do it over. So instead I'll say self.root equals try node. Okay. Now we're only adding words that don't have a period, but we're searching for words that do have a period. So, but we still need to add words like this. Okay, so for word and word, for letter and word rather, I need to say now I need to iterate through the word, which I can say self or current equals self.root for letter in word if letter in cur.children cur equals cur.children letter. So now we've moved from, if we're at B, if B is in the tree already, we've iterated over to the A node. This is a node right here. Else, if letter is not in cur.children, then cur.children letter equals to a tree node. And then cur equals cur.children letter. So this can be reduced to saying if letter not in cur.children equals to a tree node, and then this can be moved outside. So that adds the entirety of the letter. Cur.children. So we don't even need that then. For letter in word, if B is not in the dictionary, cur.letter, the letter B equals a tree node. That is the key. The letter is a node. and then we move over, we set cur equal to the new node. And then if the next letter, for example, D is not in this node that cur is now equal to, or that cur is now set at, then we keep creating another nodes that are pointing at the next node with the letter in it as the key. So that solves adding the word. But when we search for the word that has a period, that's not as simple. So we need to be able to how are we going to traverse through the word we're searching for that has a period? That is the hard part. I could say if a period is not in cur.children, also add a tree node with the period. That could be interesting. Let me see how this looks. If letters not in cur children, if period not in cur.children, cur.children period equals to a tree node, and then add the word and add a tree node. Node of type tree node. This sounds a little ridiculous to me, but add period with the word cur.children This is the remaining part of the word. This is the node. So we have the remaining part of the word. Cur equals to node for letter and word. If letter not in cur.children, cur.letter equals true node. Actually, maybe this would just call add word itself. That can't be right. If the letter is not in cur.children, set the new node with that letter equal to a tree node. If the period is not in cur.children, add the period. Cur.children, a period contains the tree node, and then we need to go to the next part of the word, which would be here. For letter and word, if letter's not in cur.children, cur.children equals a tree node. This is an actual letter. And then if period is not in cur.children, we add another period and we do the same thing over again. That looks like it's more, I think it looks more sloppy than it actually is. Okay. And then when we search for the word, for letter in word, if we say cur equals self.root for letter in word, if letter not in cur.children, then we return false. If it is, then cur equals cur.children letter, and we move over to the next part of the try, which would be A. Once we get to the end of the word, we've broken out of this for loop, and we can return true. Okay, let me look this over. Create the try node for letter in word. If the letter's not in cur.children, then we set it equal to a node. We update the cur to be the next node so we can keep traversing through the try. If the period is not in this level, then we need to add it to that level so that later we can look it up. Cur.children, the period equals to a try node, and then we go through add period again with the remaining of the word, not including that letter, by the way. And then the next letter, so say this is, say we're at B period. Say this was an A, so now we'll be at the letter D in word. So if letters not incur.children, that gets added there. And then we continue on with that traversal. But then if the period is not in this level of the try, then that gets added. And then we continue iterating again. This constraint of saying the word in search consists of, it'll be at most 2 dots. I'm sure there's a way for me to optimize this function to ensure that we'll only have a word with 2 dots, 2 periods, but I think that may overcomplicate my solution. I can't quite grasp it. So I think that's all good then. Cur equals to node, not self.root, but the next node over. Is that going to be okay? Yeah, that should be okay. And then okay, yep, that all looks good. Let's see what we get. Okay. Add period is not defined. Yes, I do mean self.add period. Thank you. It takes 3 positional arguments. 4 were given. Oh. It's going to time out. Dang it. I doubt we even reached this point. It must be that at what point do we end? We end when we're at the end of the word. If letter's not in cur.children, cur.children letter equals try node. If period is not in there, self.addWord, word, cur.children, period. I see what's going on. It's not word, because word just adds the entirety of the word. So we keep on getting the entirety of the word, and that is a never-ending loop. So it would actually be from where we're at in the word to the rest of the word. So we'll say, I need to stop saying so we'll say, but it's just in my vernacular. Anyways, we'll say index in range length of word if word index and then word index self.add period word everything from index on, and that is if I do the colon in the index, it is everything including and after, I believe. So I think I need to do index plus 1 and then word index. Oh, but I also need to do it right here as well. So if word index okay. Wait a second. This is everything before. So this is everything after and including. I'm getting an ad for AAA. My brother works there. He just was going to refer me. Okay, well, that didn't work out the way I wanted it to. But at least it didn't time out. So what case did it fail on? False. These are being added. True, false. Is that right? And this is false. One, two, three, four. This was false and it should have been true. Is my indexing correct? I think it is. This is supposed to be true. So if on the first letter, wait a second. So we add A, we add AB. If period is not in cur.children period equals a tree node, self.add period with just B. So for index and range length of B, if B is not in cur.children, create the node, but if the period, which would be at this position, is not in cur.children, then cur.children equals a trinode. And then we add the word again, but there's nothing left. What else could I do? We're searching at the end, so by this point the entire try will have developed. So we could just say print cur. We should do that before. I like that. I don't know if they've always had this function where you can click on use case and it goes over here. Yeah, that's not going to do much help. I don't know why I'm doing that. Well, A in period. Actually, that's not a bad idea. If letter is not in cur.children, return false. This one's not working. This period is working. One, two, three, four. Expected true. And this period, this A and dot are true, which tells me that we are iterating or traversing through the try and adding periods, though just not as I would have liked. Okay, we're at 45 minutes, 46 minutes. Okay, let's see if the case is period in B. Period not in cur.children. We have period, and now we add the remaining